mind. Then let's continue with MRI, so magnetic resonance imaging. So today we should discuss two-dimensional Fourier transforms.
So we start with statistical methods, right?
No, this is two-dimensional Fourier transforms for MRI. But of course, you learned a lot of Fourier transform business in statistical methods. So what we went up to last time was the MR signal equation, which took this form. And where these kxt and kyt were defined as these things. So, tell me, what do you remember? Belinda, let's start there and then go over. So, what was ST? What does that represent?
Signal.
The signal, and what is the signal? And so, what kind of signal? What? Yeah, so where is it registered? What signal? Which signal? And what kind of thing is it? What do you associate with ST? Okay, so that's the MR signal that is acquired by the receive coil at time t. And is it, what kind of thing is it? Is it a real number? Is it an integer? Is it a kangaroo? So it's a complex number. So the important thing is that it's a two-dimensional entity. Okay, what's your name, by the way? Zina. Okay, then the next thing that we have here is this integral over dx dy. So what does that refer to? Or what's the interpretation of that?
I mean, the sigma is just measured in the x and y plane, so I guess that's it. The x and y plane and the according.
Yeah, and what does the integral then mean?
The area under the curve.
Yeah, but what's the interpretation of the integral here?
Space independent.
Yeah, so essentially it's you should just view it as an average over space. So it's just the integral means just summation or averaging, because it's a summation with respect to the dx, averaging over space. And yes, it's in xy in the xy plane, but why is it in the xy plane? So this is already our simplified signal equation. So why is it in the xy plane?
Because the signal can only be received in this plane.
Yeah, that's one reason, and there's another reason. Because it could also stem from from the xy plane all over the z dimension.
we are just measuring slices and average the effect of the slice.
Exactly. So we so the idea is that what is behind this is that only a slice has been cited, but that's kind of, I mean, whether if it's a thin slice, then the slice makes sense. If it's a thick slice, then it's essentially the whole sample. But the averaging over the z axis has already been done. So that's the integral over z is already carried out here. So that was this little equation that we had earlier. So what's then the mxy?
Not sure I have to repeat this.
So do you have an idea? No?
Maybe every moment in the x, like a vector of the x and the y coordinate from the initial value.
Yeah. So there's an even easier way to say that. So if you think about the whole MR experiment, that you put something into the scanner and then what happens? Or you put it into the magnetic field of the scanner. Well, there's if you put something into the magnetic field of the scanner, everything in there becomes a little magnet itself, and you have this equilibrium magnetization, and this mxy refers to the equilibrium magnetization. So this magnetization that is induced in the sample based on the external magnetic field, the equilibrium magnetization upon its tilting into the xy plane. So that's the proton density. So this is also what you should always link these things, of course, back to what you learned in the Hüttel. So this is the proton density. This is, if there are many protons, then there's a lot of magnetization at xy. If there are a few protons, then there's little magnetization at xy. You're Fabian, right? You're Fabian, yeah. So what is then this bit here?
This spin, what's the movement of the precession?
Yeah, that's so it describes the circular movement. Definitely, that's true. And what are these kx, ky terms?
Like the movement in the x and y direction, or?
No, I mean this here. So what do these kx and ky? So the interpretation of the kx and the ky, this is actually what we will do today. But what is this here? Any idea? These were the gradients. So these are the gradient waveforms, which are linear gradients. So they are the rate of change of the magnetic field in the x and y direction. And these, as we discussed when we did things on the gradient fields, these were these are things that can be manipulated, and they can be turned off and turned on, turned on and turned off, of course. And this actually, a little bit more on this is then the topic for next session. So turning on and off, turning gradients on and off, that will be the important thing in sequence design. So today we want to basically get a understanding of this entire thing here in terms of 2D Fourier transform. So this kind of style of questioning things, this is kind of for the oral exam on this, right? So this is, so you're not necessarily, I mean, I may ask you to also write down equations, but what is even more important, that you can explain what these equations mean, and that you have a general idea about what's going on in terms of this quantitative description of MR phenomena. Good. So then the aim today is to continue essentially with the MR signal equation and now give it some meaning in terms of the two-dimensional Fourier transform. Because essentially what is written there is a two-dimensional Fourier transform. So does anyone remember the Fourier transform, the normal Fourier transform, the one-dimensional Fourier transform? So if there is some function, so let's start with Fourier transform. If we have a function for example, do you remember how you compute the value of the Fourier transform for some frequency? That's statistical methods, but and that's actually one of the questions, of course, for the exam as well. And this is a little formula that one also can memorize. Any idea? No? Good. So the Fourier transform at frequency or for this value omega here was or is defined as the integral of the function f multiplied by minus 2 pi omega x integrated over x and this for all omega r. Yeah. So you might already see some parallels between the 1D Fourier transform and this formula there. So there is some kind of function here, fx. Here we have a function in two coordinates, namely x and y, and then it's multiplied with some complex exponential. Here I actually put the I here, that's in front, and that doesn't matter at all. And then there's some integration over x. Here we have an integration over x and y, and there are some parameters. Here the parameter or the argument of the Fourier transform is omega, and here it's the kxt and kyt. So do you remember what these f omega represent? So what's the meaning of the f omega in Fourier transforms? Yeah, no, there are so many presentations. One cannot really learn anything else than doing PowerPoint bullet slides or something. So anyone remember what f omega represents, or what's the meaning of a Fourier transform? So what's a Fourier transform?
Describing so on the x-axis normally you have time and time or space, but Fourier transform has on the x-axis the frequency, so it's the integral of the normal. So it describes the pattern of the distribution of frequencies across the signal.
Yeah, so I wouldn't necessarily say distribution. That sounds a little bit like probability stuff. So it's the frequency content. Yeah, so it's f omega. So for each omega in this frequency space, f omega describes how much of a given frequency, and with frequencies you should of course associate the frequencies of cosine and sine functions, how much frequency is present in a signal. Yeah? And essentially the idea is that by combining cosine and sine functions of varying amplitudes, you can reconstruct the signal. Yeah? So that was the stuff that we did on Fourier series representations of signals, so that you can build up complex signals by adding together many sine and cosine functions of different amplitudes. And the same idea essentially holds true for 2D Fourier transforms. The difference is that we now not talk about functions that extend over a one-dimensional space, so univariate functions that look, for example, like this, where we here have time or space. But we talk about, when we talk about 2D Fourier transforms, we talk about functions that extend over two-dimensional space. And yeah, in general, this two-dimensional space, and specifically in MR imaging, models space, so two-dimensional space. So it's, I guess there is definitely some literature on that. One of them here is time and the other one is space, and you have time space on which you compute Fourier values, but the general application is for two-dimensional Fourier transform is space, two-dimensional space, or images. Yeah, so an image is a function over two-dimensional space. Yeah, so we're talking about computing Fourier transforms of images or of functions over 2D space. And the image that we are concerned with in MR, in the MR application, is our MXY. So what was MXY again?
Equilibrium.
Very good. So that's or the proton density. So that's essentially how much magnetization there is at given points in space. Of course, if you think a little bit ahead and actually beyond the stuff that we will be able to do here, we also discussed that you can do these T1 and T2 weighted contrasts, but of course, if you think about how this worked in the Hüttel, this all was always dependent on some initial magnetization. So this equilibrium magnetization is kind of the basic building block for any kind of imaging, and then you can, by setting the imaging parameters, as we discussed in the neurocognitive methods PowerPoint course, you can basically emphasize look closer at the T1 and T2 time constant properties, without going into details right now how that works. But this all is done via the equilibrium magnetization, the MXY. So this is the image function that we are dealing with. Good. So with this kind of background, let's then start a little bit into the notion of 2D Fourier transforms. So you find the stuff that I'm presenting now, you find that in the Fourier transform chapter of PMFN, because it fits better there than it fits into the MR bit. So that's where you have it. And if you are fine with 1D Fourier transforms, this is why we discussed Fourier analysis at length in the beginning of the term, then I think two-dimensional Fourier transforms is also it's not a big conceptual step. There is one important difference, which we will come to, because the basis functions are a little bit different, but in terms of the formulas and the overall idea, it's essentially very similar. The big difference, of course, in two-dimensional Fourier transforms is the fact that we are dealing with image functions. So we are dealing with formally bivariate, and in our case always real-valued functions. So we have something like this, which gets mapped to a single value fxy. And so essentially, as also shown above. What this means is that you have a two-dimensional space, R2, and to each point in the space you allocate a value, and then this allocation, if you then look at the visualization of that, this then looks like an image. So if you, I don't know, it's not really a brain. So here you can of course think, it doesn't really look like anything, but if you think about the values that are shown here, then you can think the white is a 0 and the blackish is a 1 or so, and then you have allocated to each point in this R2 or a subset of R2. So for example, if you're here on just the interval -1 to 1, you have allocated a value and then you have an image. Yeah. So bivariate real valued function can always be interpreted as images. And of these, the Fourier transform is formed essentially in analogy to the Fourier transform of a univariate function. The difference is that the Fourier transform values have are functions also of two parameters. Yeah. So a Fourier transform, a two-dimensional Fourier transform is not a univariate function, but it's a bivariate function. And these values are defined as, again, integrals of the function of interest, exactly like in the 1D case. And also, as in the 1D case, multiplied with a complex exponential. And then the difference is that instead of only having like an omega x there, we have this k xx and k y. So the two arguments of the image functions, they are multiplied with this k, with these k parameters, added and then integrated over. So, but this is really completely an analogy to the 1D thing. So think about the 1D thing. So the 1D thing is this. So it's just an additional y there. One could, in principle, call the parameters, then it would be maybe even more evident. One could call these parameters kx and ky. One could call them omega x and omega y. Then it would be the direct generalization of this omega. I didn't do that for two reasons. First of all, if you are dealing with MR, people always talk about k-space. So k in this k-space refers to these k parameters, as we will see today and also next time. So, and it's just a term that you will encounter when you encounter MR imaging. That's one reason. The other thing is that the kx and ky, they have an interpretation of frequency, but they have one additional interpretation. So they go a little bit beyond the omega. So this is why instead of calling them omega x and omega y, the parameters of f here, I call them kx and ky. Yeah. So that's the definition. And before we so this is of course for all k, y in each of them in R. Before we go and looking at some pictures and getting a little bit more intuition, the important thing for magnetic resonance imaging is of course that, like the one-dimensional Fourier transform, the two-dimensional Fourier transform is invertible. Yeah, that means if we have the Fourier transform values, so if we have f, kx and ky for different values of kx and ky, and assuming sampled in a somehow good way, then we can reconstruct the image function, so fx y, based on these values. So the Fourier, so the 2D Fourier transform is this, and then there's the inverse 2D Fourier transform, which, like in the one-dimensional case, returns the original function. And let's not define this, but if this is following from the above, as in the one-dimensional case, this looks fairly similar. The difference is that in the integral, so on the right-hand side of the equation, it's now the Fourier transform values, and then we don't have a minus sign here, and this stays all like it is, but the integration is formed with respect to the kx and ky parameters. Yeah. And yeah, this is of course very important for imaging and for especially for imaging, because if we say that the signal equation somehow gives us the Fourier transform or the two-dimensional Fourier transform of the image, then of course it's nice that we can acquire somehow the 2D Fourier transform of an image, but in the end we're interested in the image, so we need to compute the inverse 2D Fourier transform. And this is what is called image reconstruction, and this is then essentially just done by plugging in the Fourier transform values into the inverse Fourier transform. Of course, this is done in a discrete way, and we will get to the discrete way, but for the moment we look at the Fourier transform itself. Yeah?
Shouldn't that be the derivative of y in the integral? Isn't that the integral of the function the next higher order function?
Yeah, you should. You mean in terms of antiderivative? Yeah. No, you should. The way you should see that is as an average, and we will. We will actually, I will give you an intuition about what this means in a second once we go over what these functions really look like. But you should not confuse that with antiderivatives. So the integrals that are meant here are numbers, and specifically complex numbers. Yeah.
So it doesn't have to do anything with integral like we did in school, for example.
The thing is, it's a little bit unclear what you did in school. So, but in school you computed areas under the curve, so you computed numbers, and to do that you computed the antiderivative, and then you used the central theorem of calculus to compute the number that represents the that is equivalent to the integral, and the same thing applies here. So you compute numbers, yeah. So this f for kx and ky is a complex number, yeah. So it's a number. Integrals are numbers. Antiderivatives are functions, and you can also always view integrals as functions if you somehow make them, for example, our integral of the gradients. This is easily conceived as a function of t, but for a fixed t, this is a number. And the same thing here, I mean, this is integration over the entire real line, so that's a number. So the important, integrals are numbers. Antiderivatives are functions, but then it's always with respect to what is a number and what is a function, but also always depends a little bit on the context, because you can make numbers functions and you can make functions numbers. But these are integrals essentially like you did in school. Only that, that they might a little be harder to evaluate. The good thing is that they are only evaluated in terms of sums anyway, in terms of the discrete 2D, in terms of the discrete Fourier transforms. Other questions? Okay, so then the question is a little bit what is actually happening and how one can think about these exponential, complex exponential functions. And this, this is then what I want to do next. So, of course, the meaning of these complex exponentials is not new to us, because we've seen them now many times, and we know that they are closely related to cosine and sine functions. So I'm now taking this complex exponential here to look what that means. So does anyone remember what ix is equal to? No? So this is cosine of x plus I sine of x. This is, I think we discussed it last time, but we also discussed it a long time ago in when we discussed complex numbers and complex exponentials. So that's the relationship between complex exponentials and the cosine and sine functions. So essentially, this thing that is in the 2D Fourier transform and also in the 1D Fourier transform just corresponds to a cosine of two elements or two arguments plus a sine of two arguments. Oops, there's no I, sorry. Because the I, of course, is outside of the functions on the right-hand side. Yeah, so what's happening, of course, is that when forming the Fourier transform, the image function here, fxy, is multiplied at each location x and y with this cosine, with the sum of the cosine and the sine. So essentially you should view this, and I might say this a couple of times today, you essentially should view this as a correlation. Yeah, not a correlation in kind of a formal sense, but a correlation in the informal sense of if you multiply two things and they vary together, then you get most of the time large values. Also, if they completely vary in opposition to another, then you get always then you also get something. But if they if one of them, if they over repeated times, so xy, x1, x2, x and so on, don't show some similarity, then you don't get anything out. Yeah. So a very intuitive way to think about it is that you correlate the image function with these cosine and sine functions, essentially exactly as it's done in the 1D case. Now, there is a difference to the 1D case, however, because in the 1D case, remember that we talked about these generalized cosine and sine functions, which were essentially things like this, essentially. So they were just cosine and sine functions of some variable. Here we have cosine and sine functions of two variables, namely x and y. And it's very important that you understand and have an intuition about these cosine and sine functions in two variables. So this is why I isolate them here and basically show them a little bit more in detail. So there is, if you think about our generalized cosine and sine functions from the very beginning of Fourier transform business, there are generalized and cosine functions in the 2D Fourier transform business as well, but they are now functions in two variables and have this form. So I'm using this AK here just as an amplitude parameter, but it's not very interesting. We will not do much with it. The important thing is that we have a cosine that is a function of x and y, and it has two parameters, kx and ky, and they are added. And the same way we have this bivariate sine function, or generalized sine function. And here we use the bk, so these ak and bk, they're of course reminiscent of the ak's and bk's we discussed early on in 1D Fourier transform. Yeah. So these are the things that are behind this exponential, complex exponential. Now the question is, that's fine. So we have somehow we can draw these functions. So we can use x and we can use y, and then for each point in space here we can evaluate. So for example here we can evaluate cos 2 pi kx x plus ky y. So we know what 2 pi is, we know what x is, and we know what y is because we are here. But the question is, what about the kx and the ky? What do they refer to? And yeah, without further ado and without any justification, these parameters, so these are parameters of these 2D functions, like the omega was a parameter of the generalized cosine and sine functions. So do you remember what the omega referred to yeah, that was the f omega, but the omega in the cosine function. No? The lama? Ach, Lamur. The lama frequency. Isn't a lama is kind of this thing that spits. That's a lama. No, the Lamur frequency, yeah, this is something that exists, but this is not quite what I meant here. It's a frequency. So the omega was a frequency, and then remember that we discussed when we talked about Fourier analysis and generalized cosine and sine functions, we discussed radial frequencies and circular frequencies, and the omega was the circular frequency. So remember this in the very beginning of the course. So the omega was a parameter, and you could set the omega to higher or lower values, and this changed the frequency of the sine function or the cosine function into which it was put. And in the similar way, the kx and the ky are the parameters of these bivariate cosine and sine functions, but they are not only the frequencies. They are related to the frequency of these bivariate cosine functions. So if you square the kx and the ky and take the square root, then you get the frequency. So this, in this case, it's always a spatial frequency, of course, because we're talking about things extending over space, spatial frequency. And if you compute the arc tongue of the ratio between ky and kx, you get the orientation. So one could I guess one could use some way, actually I didn't go into that at all, of deriving these basic properties from the formulation, but actually it was more important to me to get at the intuition and some meaning, rather than now making more fuss about how this, where this is coming from. So what this means is that, and I will show you a nicer picture in a second, but what this means is that, of course, a cosine or sine, they make this upward and downward movement over space. So if you imagine that here you get something like this. So where the where you have valleys and wave crests or whatever. So you have something that moves like this over 2D, and how fast it moves, that's the omega. So that's essentially referring. We can also view that as the inverse wavelength. So that's the omega, and how it's oriented. So whether it's tilted as it is here, or whether it's vertical or horizontal, that's the theta. So that's kind of the angle between, let's say, a normal here and this orientation of the wave crests. Yeah. So the important thing, and this is really the most important thing about this whole thing, is that the kx and the ky, they refer to the spatial frequency of these basis functions and the orientation. So let me show you a picture that is nicer than what I've just shown you. So what this shows are cosine functions. So these are these cosine functions that we just discussed. So they are, where are they? They are here. So these cosine functions that we just discussed, now plotted over x and y, where x and y each varies from -1 to 1. And there are, that's interesting, they are plotted for various setting of the kx and the ky parameters. So for each of these panels, the title denotes the kx setting, so -2, and the ky setting -1. And what I then also evaluated is the omega parameter and the theta parameter according to the formulas that we've just seen. It's interesting, for some reason it here says this. Anyway, because it's just a for loop, so I don't know where that's coming from. In any case, what you see here is once it's settled, as the parameters change. So you see here that kx changes from -2 to -1 to 0 to 1 to 2, and ky changes from -2 to -1 to 0, 1, and 2. The layout, or not the layout, the appearance of the resulting generalized bivariate cosine function varies. Yeah. So if you have, if both kx and ky are 0, then you see that there is no up and down movement or valleys and wave crests at all. So it's constant. I mean, it's just a cosine of 0, so it's 1 everywhere. But as soon as one of them is not 0, you get some appearance, some wave-like behavior, and then it depends on both the kx and the ky, how the thing is oriented. So for example, if we have kx0 and ky -1, then it's horizontal. It gets tilted if they have the same value, tilted by 45 degrees, and even more tilted if one of them gets larger. What also happens if both of them increase is that the spatial frequency gets higher. Yeah. So this then, in general, if one now zooms out, results in this kind of pattern where again kx is increasing this way and ky is increasing this way, and importantly the 0 is in the center. Yeah? So the 0 is essentially where you have the spatial frequency of 0 because it's just constant, and then the higher spatial frequencies you find for higher absolute values of kx and ky towards the margins, and the combination of the kx and the ky not only refers to spatial frequency but also to the orientation of this function. Yeah.
Black and white in those pictures are -1 and 1.
Yeah. Yeah. So exactly. So it just goes up and down. Yeah. And this is for the cosine, and for the sine, of course, it looks fairly similar. So for the sine, it's just shifted by 90 degrees, which one can see a little bit. It's a little slow at this. So they just see the 90-degree shift. Yeah. So why am I talking about this? Because these are the basis functions that are, if you want, correlated with the image function to form the value of the 2D Fourier transform. Alternatively, you can see this as, if you think about our Fourier series again, where we used also the generalized cosine and sine functions in the one-dimensional case to combine a signal. You can also view this, of course, as the basis functions that are used to create an image. Yeah, so the idea is exactly like in Fourier series. If you know the weights for these different generalized bivariate cosine and sine functions, and some of them have high weights, some of them have low weights, then you can construct a complex signal over two-dimensional space, which is an image. Yeah? So you can build up an image based on these basis functions. Yeah, I think I want to now stop for the moment, and after the break do discrete Fourier transforms. Are there questions right now?
So the k is a function itself?
No, the k, so the k is a parameter. Yeah?
It's just a parameter, okay.
The k is a parameter. So if you're referring to the signal equation, because there the k is a function itself, there it's kxt.
But in this case it's just one parameter.
In this case, yeah, it's just one parameter, but of course there are many. Yeah, so it's like in the one-day Fourier series where it was a series, so the frequencies were running over essentially all of the values they can assume. And in this case, the kx and ky, they ideally cover all of R2. So ideally, you evaluate the weight of each of these basis functions for many values of kx and many values of ky. But for a fixed value of kx and ky, like shown here, these basis functions take one, assume one form. Yeah, so these are functions that are parameterized by two parameters, and depending on the value of these parameters, the functions look different, but of course share some similarities in the sense that they are cosine and sine functions which are extending over two-dimensional space and go up and down. Other questions? No?
I wanted to ask, so
I'm just a little bit confused. So this is like in what stage we receive it? Is it like the basis and then for receiving our image and then we apply Fourier transform or before?
Yeah, so right now we're talking basically irrespective of MR imaging. So we've just discovered when we discussed the signal equation that the signal equation, once we simplify it, looks like the 2D Fourier transform of the equilibrium magnetization. And right now we're just discussing some details about the Fourier transform so that we understand it better. And next time we essentially discuss how, first of all, when we receive the signal and how the gradients are turned on at a given point in time. So for today, try to separate this. Yeah. So we stopped a little bit with MR. We went up to discover that the signal equation looks like a 2D Fourier transform. So we decided to talk more about 2D Fourier transform to understand 2D Fourier transform more. And next time we link it again back to when we acquire the signal and when in MR imaging and when gradients are turned on.
So it's not like a stage, it's more explanation than that.
Yeah, exactly. Good, then let's have a break and continue briefly after 10 after 9 or so, with discrete Fourier transforms.